How did you guys feel about taking the test online? Was it all right? Yeah. Okay. Good. I'm glad to hear it. I felt like the scores were pretty in line with what they should have been. If anything, they were maybe a little bit higher, but that's kind of to be expected, I guess, in this situation. So I'm not going to hold it against anybody, right? Okay. So we've got to start chapter 4. And chapter 4 is about logarithms and exponential functions. You likely had some of this in an intermediate algebra class or previously in an algebra class, but I am not going to assume that you know everything. So I've slowed it down a little bit. We'll start with 4.1 today and we'll finish it off tomorrow. And then tomorrow and Wednesday, we'll work on 4.2. The plan right now is that Thursday would be like a Q&A, question and answer type session where you could ask me questions on the 4.1 assignment, which is due Wednesday night, or on the 4.2 assignment, which is due Friday night. So for the most part, I tried to make it so you just have 2 things due each week. Although I think there's one assignment a little bit later on that's split into 2 parts. So you actually have 3 assignments that week. But not for right now. We're going to try and get used to this and see how it goes. All right. Okay. So I need to share my lovely little ImageMate screen. Yeah, I am. Nope, I want to do this. This, share app. Okay. All right, you can see the screen at this point, I think, right? All right. So, there. All right. This is chapter 4. We are in exponential and logarithm functions. And for section 4.1, we're going to take a basic look at exponential functions. All right. If we let some function f of x be defined by 2 to the x power, notice that 2 is what we would call our base, and that our x value, or unknown, is actually the exponent. This is different from most of the things we've done this far, because our unknown, or variable, is actually in the exponent position. This is different than what we've done so far. Okay. All right, so you can find f of 1. F of 1 would be 2 to the first power, which is just a 2. You could find f of negative 1. This would be 2 to the negative first power, or 1 over 2. However, what would you do if you had f to the square root of 3, or f of the square root of 3? Can you put the square root of 3 in the power? Can you do 2 to the square root of 3? Austin, you said no?
Yeah.
Why not?
I guess it doesn't make any sense. I guess. Well, I mean, you could. It would just be like a decimal, so I guess I suppose it possibly should.
Right. There is an answer here. You can do 2 to the square root of 3. But the problem is, it's not tangible for most of us, right? It's not like a 2 or a 1/2. We have this sort of instinct that it's going to get to be some number. If I know what the square root of 3 is, 1.732, so this would be about 2 to the 1.73205. We could get close, and the more decimal places we included here, the closer we could get to an actual number. As a matter of fact, on most of your calculators, you can type in 2 to the square root of 3 power, and it will give you an approximation of this. So this is going to be about a 3.32. I'm just going to say 2, because usually they go 3 decimal places. Which, in a way, does make sense, because we know it should be between, well, we know it should be less than 2 squared, right? Because the square root of 3 is going to be less than 2. So we know it should be less than 4, and we get it that it's less than 4. So we can find an approximation for it. Okay? So we do want to make sure we're clear that the laws of exponents will still work even if these aren't integers. I can still do all of this even when the powers that we're dealing with are not integers. Okay? Now, we can say, by definition, the exponential function with base A is defined for all real x by f of x is equal to a to the x, where a has to be greater than 0 and a cannot equal 1. So a couple of things. We can only have positive A values. So our base is only a positive A value, not a negative A value, only a positive A value. All A's are going to be greater than 0. And A cannot equal 1. Why?
Because everything's squared to the first power, it's just 1.
Well, not squared necessarily.
Every power on the first is just 1. I don't know how to word it, but
let's say f of x is equal to a to the x, but we're going to let a equal 1. Just for giggles, right? Let's see what happens. Then our f of x is going to be 1 to the x power. So if we just plot it, and I'm just going to pick some random x values. X can be anything. I'm going to let x equal a -3, a -1, a 0, a 1, and a 3, just to get myself some points here on both sides of my xy axis. Then my y, which is the same as f of x, would be 1 to the -3rd. What you remember from your negative exponents, this is 1 over 1 to the 3rd. And here's where I catch people. 1 to the 3rd power is not 3, it's just a 1. It's 1 times 1 times 1. So I'd have a point at -3, 1. My second point, if I let x equal a -1, I would have y is equal to f of x, or 1 to the -1. This would be 1 over 1, which is just 1. And I have a second point at -1, 1. If I let x equal 0, I'd have 1 to the 0 power. Any number to the 0 power is always 1. That's going to give me a third point at 0, 1. Do you see what's happening here?
yeah, it's only 1. All the y values.
Right, because 1 to any power is always
1.
Mm-hmm. So what kind of line am I going to get?
A vertical
Uh,
or horizontal.
Yep, I'm going to get a horizontal line. So this is not any big, it's sort of the exception. It's a flat line, essentially. So we accept letting a equal 1 because it doesn't give us an interesting result, essentially. Okay. Now, let's look at some generals. In general, if f of x is equal to a to the x, this is what I use all the time when I'm doing these. That if we plot our xy, Just those 3 points, -1, 0, and 1. Knowing this little general rule can be extremely helpful when plotting logarithmic functions. Right? If I let my x be -1, then my f of x would be a to the negative first, which is the same as 1 over a. And I will have a point at -1, 1 over a. If I let my x equal 0, then I have a point at a to the 0, which is just going to be a 1. This gives me a point at 0, 1. This is important because it tells me that in any logarithmic function, I will have a point at 0, 1. In general, for any logarithmic base function, I will have a point at 0, 1. If I let my x value equal 1, I will have a to the first, and this gives me a. So I will also have a point at 1a, where a is the base. How is this helpful? Okay.
Helps us graph.
Absolutely. And it helps you graph quickly. Okay. I'm giving myself a big graph here. So we're going to graph the 3 exponential functions here. I've got f of x is 2 to the x, f of x is 1/5 to the x, and f of x is 5 to the x. So if I use this lovely little trick on this particular problem, I can see that my a value I feel like I lost something. Well, I cleaned up. I probably shouldn't have. For this one, a would equal 2. This means that I can quickly give myself 3 points. -1, and then 1 over 2. The point 0, 1, and the point 1, 2. And this gives me that exponential function. Now, you may want to use an XY chart, but you could figure out that -2 would go with 1 over 2 squared, or 1/4. That 2 would be 2 to the second, or 4. And if I let x equal 3, I would have 2 to the third, or 8. questions so far?
Like that exponential growth graph.
This would be an exponential growth graph, yes.
Okay.
We're talking about it all the time these days, aren't we?
Oh, yeah.
Okay, so what if you had f of x is 1/5 to the x power? In this case, my a value is 1/5. Using this idea as before, if I let my x be a -1, that would be 1/5 to the negative first power, which is the reciprocal, or a -1/5. My second point would occur at 0, 1, and my third point at 1, 1/5. So -1, 1, 2, 3, 4, 5, 0, 1, and 1, 1/5. This would not be exponential growth. This would be exponential decay. Yep.
So is it always going to have 0, 1 in all the functions then?
Unless there's other transformations. In the base function, yes, that will always be a 0, 1.
Okay.
If there's not a 0, 1, some sort of transformation has been done. We'll do a couple examples of that a little bit later.
Okay.
So if we're doing this last one, oh, that orange is not working. We do a -1, we're going to have a 1/5. We're going to have a 0, 1, and we're going to have a 1, 5. All right. Looking at just these three graphs, is there anything you want to notice or call out?
Like the 1/5 and the 5 are opposites. So I guess that's the same. Like if it's a 1/2 then a 2, would those be opposites too?
So yeah, I'll take a look at that in a minute. But yeah, there is a definite comparison here. 1/5 x versus 5 to the x. They appear to be reflections, growth versus decay, right? They are reflections over the y-axis. Anything about the 0?
That never touches 0.
Yeah.
It's always bigger than 0.
Y = 0 is a horizontal asymptote. And again, that's for the base function. If we do a couple of transformations on it, that can change. The asymptote can change if we're shifting the graph. But in general, you will have a horizontal asymptote. And again, as you said, the base functions always go through 0, 1. So that little graph clearly showed the two types. All right, so there is, as I believe Austin said, exponential growth. Versus exponential decay. If f of x is equal to a to the x, and your a is greater than or equal to 1, then you will experience exponential growth. That is, end behaviors. As x goes into infinity, y will also go into infinity. And as x goes to negative infinity, y will approach 0 from the top. Oops. All right, if your f of x is equal to a to the x, and your a is less than 1 but bigger than 0, so essentially a fraction less than 1, fraction or decimal less than 1, then what happens is you experience exponential decay. And in this case, as x goes to infinity, your y value approaches 0 from the top. And as x goes to negative infinity, your y value goes to infinity. Interesting to me. So I'm going to call it interesting. So if you look at this algebraically, let's say you have f of x is equal to, let's look at that 1/5 x versus f of x is 5 to the x. Now, this option would take us to exponential decay, meaning our a value or base is between 0 and 1. So we'd be looking at exponential decay or going to 0. Versus the other option, which is exponential growth. What we're asking you to see or take note of is that 1/5 here could be written as 5 to the negative 1. Right? Negative power is the inverse, so this could be 5 to the negative 1. Negative 1 to the x power, I could think of this as 5 to the negative x. Keeping in mind that if you have a negative x here, in terms of algebraic transformations, this represents a reflection over the y-axis. Of 5 to the x. Yeah?
Yeah.
Okay, so 2 things we have to do. What do I got, 25 minutes? Okay. All right, so a couple of things we want to do. We want you to be able to find identify the exponential function from the graph. So, for example, I'm going to draw a graph here. Let's see. Well, I can't do that. Yeah. Okay, that's kind of off the grid, but that's all right. Okay. Oops. And we're going to give you some points on that graph, and we're going to ask you to identify the exponential function. So if this is a graph of f of x equal to a to the x, what would a be? What is our base?
3.
Good. Austin, you got it fast. Can you explain how you know?
So you have to figure out basically what squared equals 9.
Okay, how did you know you needed squared equals 9?
So you plug in the 2 for the x.
Okay. So this point right here, if I can, this point right here tells us that f of 2 has to equal 9.
Yeah.
Since f of 2 would be a squared, a squared would equal 9, and our a value has to be 3. Now, why not negative 3?
Can't have a negative of your a.
We have defined this as all of our bases have to be greater than 0. So I wouldn't use the -3 because that's not greater than 0. And this would be f of x is 3 to the x. Braden, Nate, anything?
Yeah. No, I understand.
Okay. Beautiful. Okay. By the way, you could have also done a -2 here, right? We could have done f of -2 is 1/9. So a to the -2 is 1/9. Well, 1 over a squared is 1/9. I'm still going to get a squared has to be 9 there. So I would have gotten the same either way. The only point that's not helpful right now is this 0, 1. Just because it's in all of them. So it's not nearly as helpful as we might have hoped. Okay. All right, so now we're going to graph the function. We want to use transformations. All right. Let's try y is equal to 5 to the negative x plus 1. And then let's try all right, so let's try those two and see how it goes. Okay, so we're going to do a quick graph of this y equal 5 to the negative x plus 1 using transformations. So I'm going to start with just the base function here, which would mean we're going to look at y is equal to 5 to the x. If I look just at that base function, y is equal to 5 to the x, that's going to be a 0, 1, a 1, 5, and a -1, 1/5. So I know those 3 points are the generic points. Now, what's going to happen when I put the negative on that x? That negative x is going to reflect over we need to reflect it over y, and then what's the plus 1 going to do?
Move it up the line of 1.
So now that I've got this general sort of lightly done in pencil, I know that I need to reflect it over the y-axis and move up. Is that going to change my asymptote? Yes.
Yeah.
I now have a horizontal asymptote at y equal 1. Remember, there's a horizontal asymptote at 0, but if I move it up 1, I'm going to move that horizontal asymptote up. And in this way, I can quickly graph this sucker. Okay, we've got a y is equal to 2 minus 1/3 to the x power. I'm going to look at my base function here of y equal to 1/3 to the x. I'm going to have a 0, 1, a 1/3, 1 1/3, and a negative 1, 3. And I know that this would, in general, be my base function, or the original function. Now, what's this negative going to do?
Reflect it over the x-axis.
That is outside the function, so it will reflect over x. And that 2
Move it up 2.
It's going to move it up 2. For some of you, you may find it helpful to rewrite this as a negative 1/3 to the x plus 2. Just having that plus 2 on the end sometimes helps with the ups. All right, so when I reflect it over the x, that's going to be there, 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 and then I need to move it up 2, so it's going to be there, there, there. Do I have a new asymptote? Yep, since I slid the whole graph up 2, I'm going to have a new asymptote at y equal 2. Okay, let's try h of x is, let's do a 2x minus 4 minus 1. I'm going to start by just doing a base function, which would be y equal 2 to the x. That's going to be a negative 1, 1/2, 1, 0, 1, 2, or 0, 1, I'm sorry, 1, 2. Would be a 2, 4, negative 1. Okay. So it's going to look something like this as a base function. Now let's figure out our transformations. What happens when I subtract 4 from my x's?
We shift it right to the 4.
Good. Shift right 4, and then we're also going to shift it down 1, because we've got a minus 1. So right 4, down 1. Right, 4 down 1. Right, 4 down 1. So it should look something like that. Do I have a new horizontal asymptote? Yep. I should have a new one at x equal -1. But do you see how this one, you lose that whole 0, 1 point?
Yes.
Yeah.
Yep.
So if it's been transformed too often or too many times, it's really hard to see the original function sometimes. But the intercepts can kind of be a clue to that, but they're not always. Okay. How are we doing on examples? Did you get enough? Yeah? Okay. Do you have everything written here? Can I log out of this particular picture?
Yep. Yep.
Good. Oh, it's being a pain. There we go. Exit. Yes, please. Come back to me. Oh, Shayna, you're here too. So nice to have you back.
Yeah.
All right, guys, you got any questions for me?
No. No.
Okay. We're going to cover one of the applications of exponential functions tomorrow, and then I'll start in on 4.2, which is natural logarithms. The idea is that Thursday would be a question and answer, not necessarily an instructional lecture, but an opportunity for you to log on and ask any questions you may have. We'll see Wednesday whether or not we've covered it all in order to be able to do that, but that is my goal. For the remainder of the term, the idea is that you have 2 assignments a week, one due Wednesday night at 11:59 and one due Friday night at 11:59. I think the last week or second to the last week, one of the later sections is split into 2 different homework assignments. So you actually have something due Wednesday, Thursday, and Friday. But you may be able to work ahead on that a little bit depending upon how well you're catching on to the material in this section.
Okay.
Chapter 4 is the last, this is the only other chapter we're going to do. So just in order to sort of streamline things since we had an emergency online class.
Yeah. Yeah.
But yeah, so if you have any questions about anything in 4.1, this homework assignment is due Wednesday night, but you've got enough to get a good head start. And then that way, if you have any questions tomorrow or Wednesday, you can ask them before the homework's due.
Okay.
Okay? All right. Anything else, guys?
No. No.
Okay. All right. Hang in there. Reach out if you need anything. You have a good night. Hopefully, we'll see you tomorrow.
All right. Thank you.
All right.
Yeah, good night.
Good night.